Hello students, Mr. Courtney here. In this video, we're going to be talking about gas laws and do some calculations involving these gas laws. So we will discuss Charles's, Boyle's, Gay-Lussac's, Avogadro's, and the ideal gas law, and then we'll also perform calculations involving these gas laws. So we're going to solve problems related to these gas laws. So let's talk about STP, which means standard temperature and pressure. And it's very important that we understand what this means. If you're told that a reaction is occurring under standard temperature and pressure, that means it is at 0 degrees Celsius or 273 Kelvin. And also that standard pressure is 760 millimeters of mercury, 101.325 kilopascals in 1 atmosphere. Alright, and it is not the STP that the standard engine flush or the brake fluid or the automotive brand. So be careful with that. People tend to think STP or the automotive brand, standard temperature and pressure. So let's start off with Boyle's law. Okay, so Boyle's law describes the relationship between pressure and volume at a constant temperature. And it states that the volume and pressure for a fixed mass of gas is at a constant temperature varies inversely. So what that means, if we have a certain amount of gas at a fixed temperature, the volume and pressure will vary inversely. So if I increase pressure, I'm going to decrease volume. If I increase volume, I decrease pressure. So as one variable increases, the other decreases. So we can go with a relationship that P1V1 is equal to P2V2, where these are our initial conditions. These are our final conditions. And since the mass of gas remains the same, then the number of moles will remain the same. So P1V1 is equal to P2V2. Or you can switch it off like this. P1 over P2 is equal to V2 over V1. Alright, so that tells us the volume is inversely proportional to the pressure at constant temperature and a constant number of moles, and that K represents some constant. And an easy way to remember it is that we boil peas and vegetables. So Boyle's law is related to the relationship between pressure and volume. And remember, for a fixed mass of gas, the pressure and volume at a constant temperature are inversely proportional. Increase one, you're going to decrease the other. So here we see, as you increase pressure, you decrease volume. As you push these particles closer together, as you add more weight onto the gas chamber, it decreases its volume because adding more weight increases more pressure. Notice the temperature stays constant at 300 degrees Celsius. And as you add more weight, add more pressure to it, the volume decreases. Alright, so let's look at an example. So a gas is collected in a 242 milliliter container at constant temperature. The pressure of the gas in the container is measured and determined to be 87.6 kilopascals. What is the volume of this gas at 101.3 kilopascals? So let's look at what we're given. We're given pressure 1, the initial pressure, which is 87.6 kilopascals. We're given pressure 2, which is 101.3 kilopascals. We're given volume 1, but we're not given volume 2. So we use our relationship P1V1 is equal to P2V2. Now we're going to substitute our values into the equation. We already know what P1 is, we know what V1 is, we know what P2 is, but we don't know what V2. So this is what we get. 87.6 times 242 is equal to 101.3 V2. So we're going to solve for V2 by dividing 87.6 times 242 by 101.3, and we get 209 milliliters. Now you may be asking, why is it we did not put in the units here? Since we're dealing with kilopascals and milliliters, and the volume is already in milliliters, we know at the end our volume will be in milliliters. Now if you're asked to convert your volume to liters, you will have to do that to show how you calculate your volume. Convert your volume from milliliters to liters. Okay, so Charles's law describes the relationship between volume and temperature at a constant pressure. So you have a fixed mass of gas at constant pressure. Its volume is going to be directly proportional to its temperature. That means if we increase the temperature, the volume is going to increase. If we decrease the temperature, the volume is going to decrease. And remember, temperature is an average of the average kinetic energy of the particles in a substance. So if we increase the temperature, we're going to be increasing the volume. We're going to be increasing energy, sorry. And since the pressure is constant, then we have to increase the volume to keep the constant pressure. And if we decrease the temperature, we're going to have to decrease that volume to keep that constant temperature, that constant pressure, sorry. So these two are directly related at a constant pressure. So here we see that the volume is directly proportional to the temperature at constant pressure and a constant number of moles. That is the fixed mass of a particular gas. And that is some great constant. And we say here, Charlie Brown's Xmas. Charlie Brown's Xmas is on TV, so an easy way to help you remember it. Charlie for Charles's law, temperature and volume at constant pressure and number of moles. So here we see you increase temperature, or as you decrease volume, temperature decreases. So these two are directly proportional. And as you increase, it also increases. So notice the temperature is changing, volume is changing. As we change the volume, we change the temperature. And they go in the same direction. So they're directly proportional because we're decreasing, they both decrease. We're increasing, they're both going to increase. All right, let's look at an example of this problem. So a sample of gas at 15 degrees Celsius and 1 atmosphere has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So we start with what we're given. We're given temperature, so we're given the initial temperature, which is 15 degrees Celsius. And remember, temperature for your gas laws must always be in Kelvin, so we have to convert it to Kelvin by adding 273. So we get 288 Kelvin. T2 is 38 degrees Celsius. So add 273, we get 311 Kelvin, 311 Kelvin. We're given V1, but we have to find V2. So we use our relationship, our equation. V1 over T1 is equal to V2 over T2. And that is the equation for Charles's law. So now we substitute our values into the equation. We substitute our V1. We substitute T1 and T2. We don't know V2, so we need to solve for V2. So when we substitute our values into the equation, we get our 2.58 liters divided by 288 Kelvin, which is equal to the V2 divided by 311 Kelvin. So when we get these values now, all we have to do is rearrange our equation to solve for V2. So 258 times 311 divided by 288, that gives us our V2, and we get a volume of 2.79 liters. So here we see that we increased the temperature from 15 to 38, and the volume also increased from 2.58 to 2.79. So here we see again, as we increase temperature, the volume increases. So these two are directly proportional. Now, if you solve a problem like this using Charles's law, and you increase temperature but your volume decreased, then that tells you that something went wrong somewhere. So go back and check your problem and see where you made that mistake. Gay-Lussac's law. Gay-Lussac's law describes the relationship between temperature and pressure at constant volume. So if you have a fixed mass of gas at a constant volume, the pressure is directly proportional to its temperature. So now we're heating the gas molecules, increasing their kinetic energy. They're going to collide with the walls of a container more frequently and with more energy. But we're not changing the volume. So that means the area that they're coming in contact with remains the same. So we increase the force but we do not increase the area, so we're going to increase the pressure. So they're directly proportional. If we decrease the temperature, the kinetic energy decreases. The force and frequency with which they collide against the walls of the container will decrease. So that decreases the force on the same area, so pressure will also decrease. So hence they're directly proportional. So P1 over T1 is equal to P2 over T2. And pressure is that this tells us here that pressure is directly proportional to temperature, and this is some constant. And we must have it at a constant V, volume remains the same, and the number of moles, or you have a fixed mass of gas. Or you can say Gale drives a PT cruiser. That should be able to help you remember Gay-Lussac's law. Gale drives a PT cruiser. So here we see, we increase temperature, pressure also increases. And we see an increase in pressure, we keep the volume the same. We see an increase in pressure because we have more weights at the top of this container. We need more weights to keep the volume the same. And here this graph shows us that temperature, as you increase temperature, the pressure also increases, so they're directly proportional. And if we decrease the temperature, as we go back to 0, then the pressure also decreases. And remember, it has to do with kinetic energy and the frequency of collisions against the walls of the container and the area in which they have to come in contact with. So let's look at an example. So a 2.00 liter flask contains helium gas at a pressure of 685 torrs and a temperature of 0 degrees Celsius. Calculate the pressure in the flask if the temperature is increased to 150 degrees Celsius. So let's look at what we're given. We're given pressure 685 torrs, and we're not given P2, sorry. So we're given P1 but not P2 because it asks us to calculate the pressure. We start with a temperature of 0 degrees Celsius and then increase it to 150. So at 0 degrees Celsius is 273 Kelvin, and 150 degrees Celsius is 423 Kelvin. So we write our equation. P1 over T1 is equal to P2 over T2. So we put it into our equation now. 685 torr, which is P1, 273 Kelvin, T1. We don't know P2, and T2 is 423 Kelvin. So if we take 685, multiply by 423. So I want to get P2 by itself. I'm going to transpose the 423 and bring it to this side. Since it's division on this side, and on this side it will be multiplication. So 685 times 423 divide by 273, and that gives us a value of 1060 torr. Since we started with the unit of torr, we end with the unit of torr for pressure. Alright, let's talk about the combined gas law. So when you look at the combined gas law, it describes the relationship among pressure, volume, and temperature for a fixed amount of gas. So P1 V1 over T1 is equal to P2 V2 over T2. So the fixed amount of gas. We have a fixed amount of gas, so the combined gas law describes the relationship between these three variables. So think of peas and vegetables on a table. Then by canceling out the constant terms, the individual gas laws can be obtained. So if temperature is also kept constant, then we end up with P1 V1 is equal to P2 V2. If volume remains constant, then we can cancel out V1 and V2. If pressure remains constant, then we can cancel out P1 and P2 and then go back to get our individual gas laws that we just discussed. So if a helium-filled balloon has a volume of 3.40 liters at 25 degrees Celsius and 120.0 kilopascals, what is the volume at STP? So remember, STP is standard temperature and pressure. So we know what V1 is, 3.40. We don't know what V2 is because we're asked what is the volume at STP. We know what P1 is, that's 120.0 kilopascals. We know what P2 is because we're told that SDP, so standard temperature and pressure. So pressure is 1 atmosphere or 101.3 kilopascals, since we're already given the initial pressure in kilopascals. T1 is 25 degrees Celsius, which is 298 Kelvin. So we add 273. T2, remember it's at SDP, so that's 0 degrees Celsius or 273 Kelvin. So we have everything we need except what, and we don't have our V2. So we could go ahead, write our equation, write our combined gas law, substitute our values into the equation now. So we know what P1 is, we know what V1 is, we know what T1 is, and we know what T2 and P2 are, but we don't know what V2 is. So now we can go ahead and solve for V2. Same thing as we did before. We're going to take our 273, and we're going to transpose, so that means we're going to bring it to the other side. So in other words, we multiply both sides by 273. On this side, it's going to cancel. So we end up with 120 times 3.4 times our 273. Then we're going to divide both sides by 101.3 to get V2 all by itself. So that is 120 times 3.40 times 273 divided by 298, and then we're also going to divide by 101.3, and that will give us our V2 value, which is 3.69 liters. Avogadro's law. Now in Avogadro's law, it describes the relationship between moles, the number of moles of a gas, and volume at a constant temperature and pressure. So at a constant temperature and pressure, you have the volume of a gas, or a fixed mass of gas is directly, for the volume of a gas, sorry, not fixed mass, is directly proportional to the number of moles. So V1 over N1 is equal to V2 over N2. So as you increase the number of moles, you're going to increase the volume because it's at a constant temperature and constant pressure. As you add more particles, to keep the pressure and the temperature the same, you need to expand the gas. You need to give the gas more space. So it's going to increase its volume to keep the temperature and pressure constant. So V is proportional to N at with some constant. That is, that A here represents some constant. And we have temperature and pressure. So how many moles of helium must be added to a balloon currently holding 6.00 moles in order to increase its volume from 125 liters to 175 liters? So let's look at what we're given. We're given N1, which is 6.00. We don't know what N2 is. We don't know what our final number of moles must be. But we know what V1 is, and we know what V2 is. So first, we write our equation, because we're doing Avogadro's law, so that's V1 over N1 is equal to V2 over N2. Then we substitute our values into the equation and solve for N2. So it's going to be 175 times 6.00 divided by 125, and that gives us 8.4 liters. So that means we have to increase the number of moles from 6.00 to 8.4, and that should be 8.40. So how do we calculate, how do we determine the number of moles that must be added? We already have 6.00, we want 8.40, so the moles to be added will be N2 minus N1. So that's our 8.40 minus 6.00 moles, and that gives us 2.40 moles. So in order to increase its volume from 125 to 175 liters, we must add 2.40 moles of gas. Now the ideal gas law. When you think of the ideal gas law, it's derived from the gas laws, and it describes how the volume of a gas depends on the pressure, temperature, and the number of moles of a gas. All right, so the state it tells us about the state and amount of gas, and it is determined by the temperature, pressure, and volume. So we say PV is equal to nRT, PV nert. All right, so PV is equal to nRT. And if you remember PV nert, then that will help you remember what the equation for your ideal gas law. So pressure, P is our pressure, N is the number of moles, V is our volume in liters, T is our temperature in Kelvin. Now, how do we know what unit of pressure to use? It depends. We're given pressure. R, whatever pressure we're given, R is our ideal gas constant. The value of R, we have three different values for R. The value of R that we use is determined by the unit of pressure we're given in the problem. So if we're given pressure in atmospheres, then we're going to use this value for R, because it's liters atmosphere per mole Kelvin. Or if we're given it in torr, or millimeters of mercury, we use this one. Or if we're given it in kilopascals, we use this value of R. So pressure could, although we may use atmosphere more often in these gas law problems, but if you're given it in another unit, you can use the different values of R, or in most cases, as you see we'll do here, is that I'll convert my pressure from whatever unit it's given into atmospheres, just to keep it constant. So you just have to remember this one constant for the ideal gas, or this one value for the ideal gas constant. So let's look at an example. A 5.0 liter flask contains 0.60 grams of oxygen at a temperature of 22 degrees Celsius. And we want to find out what is the pressure in atmosphere inside the flask. So the unit of pressure is specified here. We need it in atmospheres. So we look at our equation. We need PV is equal to nRT. So we're going to look at what we have in the equation. We don't have the pressure. We know what V is. Since we want pressure in atmosphere, we're going to use R as 0.08206 liters atmosphere per mole Kelvin. Our temperature, we must convert to Kelvin. That's 295 Kelvin. 22 degrees Celsius plus 273 gives us our 295 Kelvin. But we need to find the number of moles. We're given grams of oxygen, not moles of oxygen. So we need to convert our grams of oxygen to moles of oxygen. So that's 0.60 divided by our 32 grams per mole. So that gives us 0.01875 moles. Now that we have everything except the pressure, we have our volume, or number of moles, we have R, our ideal gas constant, and we have our temperature. Now we can substitute these values into the equation and solve for our pressure. So all we're going to do now is take our 0.0, these values here, multiply them out, and then divide them by 5. And that gives us our answer of 0.091 atmospheres. And this is what the unit we wanted pressure in atmospheres. Okay, here's another one. How many grams of krypton are present in a 600 milliliter container at 1010 degrees Celsius in which the pressure of krypton is 10 atmospheres? How many atoms is this? So we look at it and we see this is a two-part problem. First, we're asked for how many grams of krypton are present. And then we ask for how many atoms is this. So we start with our equation. PV is equal to nRT, because we're given volume, we're given pressure, we're given temperature. So we use PV is equal to nRT. So we have our 10 atmospheres, our volume is 600 milliliters, and R is 0.08206 liters atmosphere per mole Kelvin. Our T1, our temperature, is 1010 plus 273, so that's 1283 Kelvin. We don't know our number of moles, So to find grams, we must know number of moles first. So we find our number of moles. So to find our number of moles, we take our PV. Now notice we've converted our volume to liters. So we had 600 milliliters, now we've converted it to liters. So we divide it by 1,000. N times our RT. So we're going to take PV divided by RT to get our number of moles, and it gives us 0.05696 moles. So now that we have moles of krypton, we need to find grams of krypton. Remember, to go from moles to grams, we multiply by the formula mass, or in this case it's an element, so we multiply by its atomic mass. And atomic mass of krypton is 83.8 grams per mole, and that gives us 4.77 grams. Now to get our number of atoms, we multiply by Avogadro's number. We have a certain number of moles. To go from moles to atoms, you multiply by Avogadro's number, and that gives us 3.43 by 10 to the 22 atoms of krypton. Now, the ideal gas law can be used to solve almost any gas problem. So if you have a gas at constant temperature and a constant number of moles, so that means we're keeping N and T constant. N and T constant. Now, since the R values are going to be the same, then we can cancel these off. So that means P1 V1 will be equal to P2 V2. At constant number of moles, so we keep the number of moles constant, so we can equate these two values. So that means P1 V1 over T1 is equal to P2 V2 over T2. Now if we keep pressure and volume constant, so remember here that NT is equal to pressure divided by PV divided by R, Since this is going to be constant, we can keep our final and initial, final and initial conditions equal. N1 T1 is equal to N2 T2. And this is the same thing we're doing here, because we're equating the number of moles at constant N. So we put in N is equal to those values, P2 V2 over T2, or P1 V1 over T1. Since the R value will be the same, it will cancel out. These values will vary, so they're going to be equal. They will all be equal to N. They'll give us the same value. When we multiply P1 by V1 and divide by T1, the value we get will be the same as when we multiply P2 by V2 and divide by T2. So how do you know when to use the different gas laws? You have to look at what you're given. If you're given changes, initial pressure, initial volume, final pressure, final volume, or something of that, then you're going to use this gas law. So we're going to use a relationship between pressure and volume. You're given number of moles and temperature, you get to use this. Now, if you're not given a change, so you're given pressure, volume, temperature, and as to calculate number of moles, then you know you're going to use PV is equal to nRT. So you just have to look at what you're given in the equation, refer back to your gas laws, whether it's your ideal gas law, Charles's, Boyle's, Avogadro's, Gay-Lussac's. Just have to look at the variables you have in these equations compared to what you're given. So it is important that you know the variables involved in these gas laws, that you understand these gas laws. Okay, so this takes us to the end of this one. Until the next time, I'm out. Blessings.